Yeah. Was there a question or that was some noise? Okay, let's assume it's noise. So I started recording again. So you can, let's do it again. So you go to this Simulink and then you can click this blank page, and this time it's faster. So the first time it was slower, but this time it's faster. So you'll get this page, and so the first thing you would like to save, so you can save it. So there are many options again. So let's save it. It's a simple thing, and I will name it as exercise 2. And this time it will save as .slx. MATLAB script is .m. This is your .slx. Okay, so it is saved. And then you need some components. So yeah, so for component, you should go to library. Yeah, just to find books, you have to go to university library. So if you want to get some components, you want to go to library. You can go to library. Then you see these options. So there you can see your university has provided a lot of libraries for you. And if you are using your remote desktop, then I would say you do not have many options for library there. But I'm not using remote desktop. I'm using the MATLAB from on my own laptop. But this laptop, of course, this license is of course provided by the university. So if you want the license, you can simply go to this MATLAB IPM set Universtock. You can send an email. There should be some contact person. Yeah. Can I translate this? I don't know much German. Okay, so you can go here and then I think you have to send an email to software.
There's an email that says software at.
Yeah, so I'm just trying to find it on the.
It was on the previous page.
It was there?
Yeah. And scroll down a bit. Yeah, under verse 9. Yeah.
Yeah, this one. Yeah, thank you. So this is the email you send from your student email address that you need a license for your course or anything. Just you can request it anytime. Then they will give you the informations how you can install the license, how you can install the MATLAB, how you can activate the license, everything they will tell. Okay. So you can do that and you have more options for your library there. So that is advantage. So I'm using that MATLAB license. Okay, let's go to our model. So you have this library and you can see that there is like a lot of elements. So if you want to do simulations for your basic things, you can check in this library. This is for basic things. You want to do some audio, I don't know what you want to do there. Communication toolbox, computer visions, control system toolbox, DSP, fuzzy logic, fixed point designer, HDL coder, Simscape. In Simscape, you will have the Simscape electrical library where you can simulate electrical circuits also. Yeah, so you can simulate electrical circuits also. You have a lot of components. For example, here if you go, you have some electric source. You can use the voltage and current source, three-phase source, DC source. You have a lot of elements here, resistance, inductance, load, so many things. Then you can have some machines also. You can use synchronous or asynchronous machine, DC machines. So many options, excitation systems. And measurement, you have some current measurement, impedance measurement, voltage measurement, all these things you can find. So there are so many things you can do with these libraries, but we want to do very basic thing. So we'll just do some basic, we'll just take some basic things. So this is the library where from The Simulink library, we will basically have, I think, all of the components here, and let's do it. So what we want to do is we want to do the same Park and Clarke transformation from this Simulink. Whatever we did with the MATLAB script, we want to do the same thing here. So yeah, so here you do not write any code. You do everything with your block diagrams. Okay, like you have studied the block diagrams in control systems or something. We do everything with the block diagram here. For example, you want to simulate the angle. Okay. So you want to find the angle. So what we know is your angle is equal to omega t plus phi naught. Correct? So, and so if we know this omega t, we can simply add our phi naught. So how do we get omega t? So you can clearly see this omega t we can simulate from the integrator. So we have one constant block which is omega. Then we integrate this, and from your mathematics this is going to be omega t. Right? Have you ever tried from your basic high schools, I guess, you would know that if you integrate this and if a is constant, you get like 80. Sorry. So now we do the same thing. So what we need is one constant block. So you can go here and here, you have this block as a constant. And you can, of course, do the right click and add it. So you can do add block to the model. Yeah, you can do right click and then add block to the model. And then you have this block. Okay, and now we want the integrator. So do we see integrator? Yes, we have integrator here. We add it again. So for adding the elements, there are many options. You can do like that. You can go to library. You can search where the elements are, and then you can you can add those things, or you can basically search here. So you can write constant, press enter. You would see the block. So there you can see there are like maybe more than 1,000 elements. And if you want to search your element, then this is one shortcut you can use. Okay. Or if let's say you're expert in Simulink now, you know where it is and you know the name of blocks which you want to add. So what you do is you simply do the left click on your screen once and just type it. You type the name. So just type constant. One moment. So you just click and type constant. Try this. Just click, type which block you want. So constant. And then you press enter. Ta-da, I have constant. So if you do not like to go here, searching the element and adding again and again, then you can do that. So I do this more often. Okay, so I basically want integrator. So I just click and I type integrator and integrator. Then I just click, I have integrator. Everyone is able to do that? Yeah, cool. Okay, so let's do it. So the very first thing is we wanted to get the phase angle. So we put omega here, and our omega is 2 into pi into 50. Okay. This is our omega 1. And we connect it here. So you can simply click it and then drag it and connect. And you can, of course, you want to name something, so you can name it like, you can double click on the wire and you can name it omega 1 or something. Okay. Then what we want is we want to add the phi naught. Okay. So we need a summation. So do we see a summation here? Yeah, we have a summation here. We can again do the add this, or you can click on the on this page, and then you can just as summation, which is sum, and then you click, it comes. It's your wish how you are doing. Let's say we add this, and we need another constant for adding the phase. So I type constant, then we get the phase, and we add it here. So this is your phi naught. But remember, phi naught in radian. You should do everything in radian. But let's say you do not want to enter into radian, you want to enter into degree. Then also you can do it. What you do is you find a gain. It's called gain. Okay. So it's called gain. You can just click on the gain, and then you add it here. And you can do from radian to degree conversion. So that's pretty simple, right? You can multiply with 180 by pi. So this is phi naught in degree. Clear? So let's say this is your initially some degree 0. We do not want to add any phase. So this is your phase now. So you know this phase. Now you want to find these VA and VB and VC. So we have to do the cos of this angle, right? So we have to do this cos, and you can go here, find the cos.
Professor,
Yeah.
in the gain block, is it not pi by 180 for radians?
Oh, sorry. Thank you. Thank you. Then we search for the cos block. Yeah. And then we get the cos of this angle. So you can find the cos, like searching cos. You can also get it like this. And in this block, if you double click, you see many options. You can do cos, sine, a sine, a tan. So this a means inverse. If you have a before, it means inverse. But we want cos, so let's use cos. Okay, so this is for the first phase, and then we want to multiply the gain. So let's add a product. We want to multiply the amplitude now. For amplitude also we use a constant. So let's say our amplitude is 100. This is V plus. So what is this value? This is our VA, right? We want to get VB now. So to get the VB, what we do is whatever angle we have on the top, we basically do minus 2 pi by 3. And then we repeat the same thing. And for the for the C phase, what we do is whatever angle we have here, we basically add by 2 pi by 3. And then the same thing. Okay. And of course, you can have a habit to press Control S to save things. So this is your VA, VB, and VC. And now we want to see these results. We want to see how they look like. So then to see the graph, like in MATLAB script, we had a plot to plot the graph. In this, we have something called scope. So you can go to the sync, and in sync, you will find this scope. Or else you just search a scope and you see the scope. So it is like your oscilloscopes in your lab. Then you add it. So now we have how many inputs here? 3 inputs. And you want to see the results. So for sure, one input you cannot connect. If you want to see everything in one graph, then it's not possible to see using one input. So what we do is we double click. You see these settings? In the settings, you can change number of inputs for the scope. So we want to see 3 graphs. So we just connect 3 and then enter. You can resize this whichever way you want. Okay. And then you connect it here. So now you can see your ABC plot. And before that, you have to do some settings. You have to change some settings. So you go to modeling, model settings. And here you see some options. So these are the very important things you should configure before doing your simulations. So let's do the simulation and see the results. How does it look first? Okay, then we will do the settings. So this is without changing any settings, and we are trying to run the simulation. Do you think it is a sine wave? It's not, right? It's not a sine wave, but we wanted to have a sine wave. So this is, so your model is right, but your configuration for the simulation is wrong. So you should choose your simulation step time. So it is like the time it takes to compute things. So you should make it small, right? Then only it can make the perfect sine. So what you can do is you can do variable steps, you can do fixed step, but let's do fixed step. It's very simple. And then you make the step time as probably 10 microsecond. Okay. So after every 10 microsecond, it will update the thing. It will update the signal. So you can find the settings by going to modeling, and then you will get this setting. You can click it here, and then you can change these settings. You can play around those settings for sure, and then you can of course run from here also. So let's run it now. You see something different happening, and if I zoom in, you can see it looks like a sine now. Okay, so configuring your settings correctly is also very important. Okay, now we see the waveforms. But which one is my A voltage, which one is the B voltage, which one is C voltage? I don't know, right? So for sure you can add legend. So you can see this view. You can add legends. So you can add legend. And you can already see it's labeled with VA, VB, and VC. So why it is labeled? Because we wrote on the wire VA, VB, and VC. So you can label things like this, or if I remove it, let me remove this. Now there is no label on the wire, then I would expect you do not see VA, VB, and VC. So it will just show you some value, some alphabets or something. Yeah. So, and then what you can do is you can click on this, and you can basically update it. You can write VA, then you can click on this VB. You see, and the interesting thing you might have observed that all the graphs are gone. So it is true because you have, if you click this, so if you click this, if the graph is there, it will go away, and if there is no graph, it will come away. It will come again. So you can basically see all your graph, or just you can just see few of them also. Okay, cool. But now there is another way you can see your values in a scope. Instead of using 3 different wires, you can mux these things. There is a mux. So you can mux it. So this is a mux which makes many signals into one channel. It's basically, let's say you have a lot of wires, you have 10 wires or 3 wires, and you just put it in under one tube. It's like these cables, there are many wires, and then you have just everything in a tube. So that is what mux does. So you can add 3 inputs. So you can click on this, and you can put the number of inputs. Then you connect them, and you just use one scope. So in this way, now it is possible that you can use just one scope instead of this 3 input scope. And you can also see the results on that. Yeah. And for sure, you can see label also. You can see the legends also. So the first one will be the first channel which is there in the mux. I mean, it will be this. The second one will be this. Third one will be this. So you can like that. Or else you can simply write the name here, VA, VB. I don't know if it works, but let's see. VC. Let's see if the legend has changed. Yeah. So you can see the legend has also changed. So I find this way very easy, that you just label these values and then you get the label directly in your scope. Okay, so this is more handy and more easy. So is everyone able to get this? So try this and get it, okay? I'll give you some, maybe 5 minutes or something, you try.
So could you show us the model settings that you have changed for the runtime?
What did you say? You mean this runtime?
In the model settings for changing the runtime.
Which runtime?
Okay, the fixed step one. Okay.
Yeah. So this you try to keep it at least 100 times less than the frequency of your system. But the less you make, the better it is. But the less you make, your simulation will take a long time to finish, because it has to do many computations. And for sure, we do not want to see many waveforms, so we can just see the waveforms for 2 time period, So just I'll put 2 time period. I do not want to see all the results, like many waveforms. I just want to see 2 waveforms. Then I just put my stop time for two time period. So you can decide how much long you want your simulation to run. So I will just see 2 waveforms now. Okay. If you want 1 waveform, you'll see 1 waveform by just changing this. Okay, let's see. Everyone is able to get this waveform. If you can get this waveform, then I think it will be easy to proceed further. Everyone in Zoom meeting also got it?
Yes.
Okay, cool. So here also majority of students have got it. So let's proceed. And for sure it is recording, so you can watch it. You can watch it later also. So this is your positive sequence. Now we want to do the Clarke transformation. So for Clarke transformation, there is a very simple thing. You just type ABC to DQ0. Like, and then you have many options here. These are for transformations. So you can do ABC to alpha beta 0. You can directly do that. Yeah, you will get this, but do not use this, okay? You can use it. It's correct. I'm not saying it's wrong, but we will make it by ourselves. So you can simply put this thing here. Okay. So let's do it like this. So this is your VA, VABC. This is your V alpha beta and 0. And if you try to run this, for sure you will see waveforms like this. But if you have many scopes, many channels, then you can click on this below. I don't know what it is, but let's say this below cursor, and then you can click on this, and you can choose how you want to see your scopes. So if you want to see your scope in 1, just click 1. If you want to see your scopes in 3 channels, you can click, and then you will get 3 channels. Okay. So now this is your VA, VB, and VC. It looks funny. It looks really funny because it is like this dotted. So you can, again, you can do beautification here, you know, like you did in your MATLAB script, you can do your beautification here. So you can click, right click and do style. You can change the color. You can choose whichever color you want. I don't know which one. You can do like this. And then you can see it's the first scope. Then VA selected. You can change the width of this. So you can make it 2. And you see this marker. So this marker is actually selected. That is why it looks that fat. But I just unselected the marker and it looks like this. And you can change the thickness. You can increase the thickness. You can do it the way you want. Okay. And then the next one, you can do the same thing. So I just don't want to see that. 2. And then color is proof. You can change color also. Then the C, none, 2, and apply. Okay. And the same thing you can do for the second scope. This is your second scope. You can go here. And then you have 3 options. So we have alpha. The first one is alpha. You make it 2. The second one is beta. You make it 2 again. The third one is 0. Okay. And then we do not have the graph in the third one, but we'll get it. And you can also go to settings, display, and you can add title. So the first one is your VABC. Second one is your V alpha beta and 0. And the third one is going to be your VDQ 0. Can apply. And you can already see the names. But why I do not see VABC? Probably it is hiding this. Yeah. You can also add a Y label. You cannot add X label because X label is always time here. You can add Y label. And where it is. Mhm. Yeah, you see the Y level here. So you can add V dq0 in volt, and similarly you can add for volt, V alpha beta 0 in volt. Right, you see this alpha beta does not look nice, because when you write underscore it takes like it takes something different, like it takes as underscore itself. So let me write like this, V alpha beta 0. Okay, looks funny, but let's accept it. Okay, so as I said, we do not want to use this. We want to use our own model. So what we do is, first we have this mux. We want to basically get the same model which is inside. So we had a mux. Now to get the signal, 3 signals out of this, we need to use dmux. So dmux can help you to get the signals out of the muxed signals. Then we do a 3 output. We connect it here. And of course, this is our VA. This is VB and VC. Now you have to see your matrix. What is our Clarke transformation matrix? So we do not want to use simplified version. We want to use the actual. Okay. And this is our actual transformation matrix. Yeah. So we'll try to implement the same thing. So the V alpha is VA minus half of VB minus half of VC, and then multiplied by 2 by 3. So we do the same thing. So we add a summer. You can change its plus minus by adding many things here. Okay. So you can just double click on this and you can add as many summations or something you want. So for example, here I have 2 things, so it will just show me the 2. Yeah, but we want 3, so let's add 3. So we have VA minus 1/2 of VB then minus 1/2 of VC. So this is our V alpha, right? It's VA minus half of VC and half of VB. Like, so basically the subtract of those, and then we have to multiply also. So I forgot the multiplication. So it's 2/3. Yeah, so 2/3 into this equation. For the beta, we have 2/3 into square root 3/2. So we'll just do the same thing. So for beta, I try to copy this. Okay, so there is one more thing. You can copy the element very quickly by just clicking on just click on that. Then you do the right click and drag it. You click on anything, right click and then drag it. Or simply go right click, drag it. You have to hold it, right click, hold and then drag. Hold, drag, hold and drag. Okay, so you can do this way to copy things. It's pretty quick. Okay, so we need 2 minus. So you can just remove that. You get this 2 minus. So now it looks different. So we do square root of 3 over 2. So for VB, VC, for VB it's positive, for VC it's negative. Yeah, so it is square root of 3 over 2 and then minus of your VB and VC. So we implemented this. Now again, this thing. So this is our V alpha. This is our V beta. And for V0, we know it, like we basically add everything. You can simply write 3 also here. So if you write 3, it means it's a summation. If you want to get minus, then you have to write minus. If you just want to do summations, you just write 3. You get 3 inputs. Yeah. So there are so many things you can actually play around. So we basically add VA, VB, and VC. And this is our V0. Then we do the mux again. So we take the same mux and we add it here. Okay. So this is our Clarke transformation. So this is our VABC as an input. And we do our Clarke transformation. Okay. So if you do not want to see this, this messed up circuit diagram, you want to see something neat in the waveforms, what you can do is you can create a subsystem. So you can basically select it. So you can do the left click on the page, and then you drag it. So it selects the thing. Okay. So you do the left click, drag it, you select the thing, and then you do the right click, and you would see some options. So yeah, you see this thing, create subsystem from selects. So you can click on this. Now you have a system, the subsystem, and you can name it like a Clarke transformation. You can name it as a Clarke transformation, and then this block and this block, they are the same basically. Okay. And of course, you can edit the name the way you want. You can press shift, you can shift and enter to go below. You can write ABC2 alpha beta 0 frame transformation. And now let's see the results. So you can again mux these two. And now we run it. You would see they overlap on each other very, very nicely. Yeah. You can see the graphs here. It says Clarke transformation and these things. And for sure you can label them. You can change the label. So I'll give some work to you. Is this clear? Now let's try to make this block. Yeah. So take few minutes and then make this block. Oops. Yeah, demons. It's lots and then demons. DE. Go inside. So here you can see where you are.
Yes. Das one that we
Does not have. Because it is an electrical, safe electrical library, and it does not have electrical library. That is why you should send them an email if you don't know.
So, okay, you multiply by this one. Then you plus together. And then you, this game should be, two.
So this you can see. So
Should have one boy,
One over
one over three there.
oh yeah. Oh yeah. Yeah. So there is a mistake. So we should have a 1/3 here.
Yeah.
Yeah, thank you again. Yeah. Yeah, now it is correct. Okay, so now let's do the one thing, the part transformation. Okay. So let's do the part transformation. And for part transformation, you need angle again, right? For part transformation, you need some angle for doing the transformation. So you can generate the angle the same way. You do it here. So I'll just take it. Just select everything and then right click and drag. So I got the copy of this. Okay, so you can select everything and then right click and drag also, it copies everything. And then I name this as omega 2. And this is your gamma naught. So this is my basically the theta p or part transformation. So let's write part theta part. So again, we want to use a demux, get the 3 signals. Since we have muxed every signal, that is why we use demux. If you think you do not want to mux the signal, then you can use them as it is. But it feels nice when you have one input and one output. Yeah, it makes things look nicer. So we again do so we take the input as alpha beta, okay, and this is our angle. You can find the cos of it, and you can same thing, use the sine. You can have the sine of this. You can go there, double click. You can change the function to sine. And then we again implement our matrix. So for part transformation, this is our matrix. So we have cos theta, sine theta, and then minus sine theta and cos theta. So it is cos theta into f alpha, sine theta plus sine theta into f beta to get dq. Okay, so let's do that. Or I keep it side by side. Yeah, so let's do it like this. So this is our v alpha. V beta, and V0. So we want to get D, so we multiply alpha with cos and then beta with sine, and we add it. So we got D, and then for the Q, we do multiply the alpha with minus sign. So we do the minus. Yeah, the alpha with the minus sign term, and then beta is with the cos positive, and then again we add it. So this is our D. This is our Q. And you know that for zero sequence, it's the same. So you can use the same. Let's mux it again. 3 inputs. So the first one is our D. Second one is our Q. And the third one is 0. So 0 sequence is same. And then, of course, we can select this all again. And we can just create a subsystem. So this is your Clarke transformation. Which means alpha, beta, 0 to DQ's 0 transformation. And you can see one more thing, that you can give the name for the inputs. Okay, if you do not give any name, it will show some number. So you can go there, you can click it, and you can give some numbers. So you can give it, like, you can give the name, you can type whatever you want. So VDQ0. Okay. And now let's see the result. So of course, for DQ transformation, also you have a inbuilt block in Simulink. So you type DQ0, and then you see many options. So, but what we want is alpha beta to DQ. So you can choose this alpha beta 0 to DQ. And then, yeah. But remember, there is one very, very important settings here, which you should be careful. So I would like everyone to see here. So there is one setting here which you should be very careful. You double click on this, and you see this option. So it says 90° behind if phase A. So you should change this to align with phase A. Because what we have done, all the derivations where we have assumed the the average system is aligned with the A phase. I mean, the A phase is taken as basically reference for angles and all. So you don't want to add 90° on that. So you can change this to phase align with the phase A.
It's like as we have always consider alpha on align with the DA, which is the same.
No, DQ axis rotates. Alpha beta axis stays where it is. So that's a stationary. So for sure, it's not always aligned. So what it means, like align with phase A means it's basically at omega t equal to 0. So it's initial phase. Initially, it is on the same level, right? initially DQ and alpha beta. So the DQ axis, the D phase will be aligned with the alpha initially, but then they start rotating. The DQ start rotating. It's just one setting, just keep it. Otherwise, you use this block and you do not change these settings and you expect some results, you don't get the result. So you should be careful. And then you can use the same block like this. So you have this alpha, beta 0, you have this angle. And then we see the results from these two. Okay. So tell me, what do you expect? Do you expect the DC? Or what do you expect? You expect DC and you will have only have D component, or you'll have Q component also. Yeah. Correct. So here you can see there is just D component, and that is 100. So you can do beautification again. I just try to tell you how you can change things so that you make your graphs nice when you do presentations or you present or you make some reports. But I think it's clear, right? Okay. So if I add some phase here, let's say pi over 3, then do I see some, I will see the DC, but these values will not be the same. So you would see they will change. Oh, sorry. Not there, here. But I should write in a degree, right? 30 degree. Then you will see some difference. And this one is 0 value, so you'll see 0 value. Okay. And if I make this and then the gamma naught as same, I make it, let's say 30 again, then we will see only DQ. We will only see D, we will not see Q. Because now they are same, so they cancel out also. You can see the equation and you can play around these. Okay. Okay, so there is one last graph. So the last graph is your XY graph. Okay. You want to see the alpha beta graph also, right? So for that, you can use the XY graph. So you see this. So you can again go to this sync and then look for this XY graph. So let's add it. And we want to see the alpha and beta. So I think above is your X graph and beta is the below one. So let's do it. So we add dmux again. This is your X, this is your Y. So let's run the graph. When you run it, you will see something like this. This is from XY graph. But it's wrong, right? We do not see anything. So you have to change settings for sure. You have to change the limits for these things. So you have to make it like, let's say 150. This is as 150 minus 150, then 150. Now you run this. Did you see that? Did you see it making circle? It is circle, by the way. So let's do it again. Yeah. And it started with 30 degree because I gave the phase as 30 degree. If I make this 0, from where it should start? It should start from here. Yeah. So these all things you can see. Now let's make a fault on the B side. So I just remove this voltage. Okay. Yeah, so I just remove this voltage, means there is no voltage. You just can multiply with some constant. So let's say constant. So this is to simulate your fault. So if you make it 0, it means the B phase is gone. Yeah. So you would see graph like this. You see this? This is the same graph we saw, right? In the MATLAB script. It looks nice. And the same thing you can do, of course, with the phase C. Let's say 0. Then we would see the fault on this side. Okay. Let's say we have fault in both phases, B and C, the two-phase fault. Then what do you expect? There's no B and C now. There's just A. What do you expect? I would expect just a straight line in the A phase. Because if you draw the phasor diagram, no, not the phasor diagram, state space diagram, and you try to find the resultant, there's just A. So it will be like, but if there is a magnitude, let's say 0.4 and 0.4, then it would look like some ellipse. So here we have fault on both the A and B. Oh, sorry, not A and B, B and C. So if you have fault on both B and C, you will see graphs which will align to A phase. And if you have fault on, let's say, A and B, then you would see it will align with the C phase. So you can try everything. So I would ask you to try everything. So let's say we have fault on the A and C. So we would see the space diagram on along the B side. This is a state space position for the B. Yeah. Okay. So now the time is up, and so we try to do alpha beta graphs and all. So now the homework for you is for sure, I would like you to try all the harmonics with the same thing. So now what you have to do is, this is your fundamental. Yeah. And you want to you basically want to make the harmonics also. So you can copy this whole thing like this. Then you add a gain and you multiply with the harmonics here, like that's a fifth order harmonics. Make this magnitude less, so let's say 10, or let's say 20%, 20. So this is my fifth order harmonics, correct? And then you have to add to this voltage. So I really don't want to look this big waveforms. So what I will do is I will create a subsystem for this also. So Control Z gives me subsystem. And of course we need to add these things. So So now we have fifth order harmonic and the fundamental component. So let's see. You see something like this? 1, 2, 3, 4. So it has only 4. Oh, it's a positive sequence. Sorry. So for negative sequence, you have to reverse this sequence, right? No, no, no. It should happen automatically, right? Oh no, because this is realized in a different way. This is realized in different ways. So you should not multiply by 5 times here. You should actually multiply 5 times here. Should multiply the whole phase by 5 times. So if you do not want to change 5 times in many places, you can use product. And then here. You use one constant to define your harmonics. So let's say fifth. Then you multiply the phase. So here we have to multiply the whole phase by the factor, right? For the harmonics, we had to multiply the whole phase, even including these things. So you can look into this and in a script, and you would see your alpha beta graph like this now. So this looks like our fifth order harmonics. Okay, so you can change your harmonics over there. Yeah, so you can make it 7 order harmonics and then run it. Okay, just one last thing. I remove this harmonics. Now I want to realize a symmetrical fault. So that was unsymmetrical fault. And yeah, so instead of giving this as a constant, let's say this gamma, let's say one thing first. So instead of giving this constant, we give a step. And initially we do not give any phase. So you can use this step to realize two different instances, different values. And here we give some phase, 2 pi by 3. So initially for time 0.02 second, it will be 0. Then after that, it will change to 30 degree. And so there is no negative, there is no harmonics. And you can see after 0.2 second, 0.02 second, your D and Q value has changed. So it is expected because you added the phase into the system. Yeah. You can do amplitude jump also. So the same way. So I can add a product over here. So initially I keep it 1, and then after that we make it 0.5. So it means for one time period it will be 1, and then after that it will be 0.5 times the 50%. And you would see like this. So your magnitude has jumped. Yeah. So when your magnitude has jumped, also you will see something like this. Your magnitude basically falls down. But why do we see Q component? Because we have a phase, sorry. So let's say the phase is not there and there is a magnitude jump. Then you see the jump in D frame. But there is no phase, okay? There's no phase difference. But if there is a phase, you will see something like this. So something like this graph also can be given, and you would need to understand what's happening there. Whether it is a magnitude jump or what jump, so those things. Okay. Okay, so this is all about transformation, and then you should try a lot of things. You should really try a lot of things like fault condition, magnitude jump, phase jump, your harmonics, fault in different phases, and yeah, so you should try all these things, get expert with that. So generally what happens is we do a test after the one thing is complete, so that this, I said you 3 parts will be there. So the one part is done. So in normal case, we will have the test in the next exercise, but we will not do that because Mr. Neumann is not here. So he's our main instructor for this course. So when he will be back, so he will be back on 16th. So probably we do the test not next exercise, but exercise after that exercise. And here, what you learned about harmonics, phase jump, magnitude jump, your negative sequence, positive sequence, alpha beta frame plot, and yeah. So whatever we did here, you will have a test for that, of course. And then, as I said, like there will be 4 tests, and you have to pass 3 tests to qualify for the exams. But I think if you have followed these sessions, then I think you are good to go. Okay.
So, we have the test in single. Or like,
No, there will be questions you have to answer, like MCQs.
okay.
I think so. Maybe
So written, like.
yeah. It will just take 10 minutes, 15 minutes, not much. Just to check your understanding, whether you have understood or not. But these things are taken for your prerequisite for exams, final exams. You'll not get marks for this in a final grade, but these are just prerequisites. Believe me, it helps you to prepare for the final exam.
The final exam is like.
Written again. Again, you'll have some MCQs, some writing stuff, but I don't know, due to Corona, something has changed, but yeah. So I will stop recording now.